Since my previous video, the audio cut off on this example, so I just wanted to go through quickly what I did. So the reason I picked this problem is it's similar to a WebAssign problem that you have, so I wanted to kind of have something you could rely on as a good example. So we're given the cross-sectional area of the wire, and I converted it to square meters, right? So I was given it in square centimeters, so I convert that to square meters, and I'm given the diameter in millimeters, so I'm converting that to meters as well. They tell me that there is a potential difference of 9 volts across the wire. So the first part is asking for the capacitance, the charge on the capacitor, and then the electric field inside the capacitor. So this is kind of like our, kind of like a plug and chug, but it relies on us finding out what the capacitance is to find out the charge, and then using the charge to find the electric field. Right, so we've got expressions for all of these, right? The electric field is in terms of the charge, capacitance is in terms of the charge. So I'm going to look for the capacitance first. So I have the permittivity of free space, that constant. I'm given the cross-sectional area and the diameter. So it's just epsilon naught times A over D. When I calculate that, I'm in units of farads. So I get 5.31 times 10 to the negative 13 farads. So I'm calling this picofarads. So 10 to the negative 12 is pico. I think most of the time we just get asked to memorize up to, like, or to nano, or mega or something like that, but this is an abbreviation for 10 to the negative 12. So I'm rewriting this as 0.531 picofarads. You don't have to do that, but it's just something that I do sometimes. So the second part was asking for the charge on the capacitor. So I take the capacitance that I found from part A and then multiply it by the voltage applied, and I'll get the charge on the capacitor, and I get 4.78 times 10 to the negative 12 coulombs, or 4.78 picocoulombs. Final part is asking for the magnitude of the electric field in the capacitor, and so now that I have the charge from the second part, I can use Q over epsilon naught A to find the electric field, and that's what I do here. So I substitute this value in for the charge, epsilon naught in again, the cross-sectional area here, and I have a very strong electric field, right? Very small capacitance, but a very large electric field. So 3600.8 newtons per coulomb. So again, it's a pretty, it's a pretty straightforward problem as far as giving us enough information. But like I said, with the audio going out, I thought I'd come back on and kind of give a nice narrated walkthrough of this problem. So chapter 18 is going to be dealing with this expression a lot, but we're going to be dealing with capacitors in circuits, so combinations of capacitors. So what I like to do is I like to have this written for voltage and capacitance, right? So I would divide both sides by C, I get V equals Q over C, or divide both sides by V, I get C equals Q over V, because this rule right here is going to be used often for the first part of chapter 18. Okay, so everything is up there. 17 is up, and assuming you can hear me right now, all of chapter 17 and 18 are up. So get in touch if you have any issues and let me know. Alright, thanks.